variability. What I'm going to talk about today is a specific application to a place very far away from here and very green. You can tell it's far away because it's so green. But what we did was we used this very, very small location, Hubbard Brook Experimental Forest in New Hampshire. We used it as kind of a microcosm to look at the different sources of uncertainty in developing climate projections for a very, very small area. The premise of this study and of many studies is the fact that climate is changing relatively rapidly right now, and human activities are the main reason why. So if we're looking at the long-term sustainability of almost any system that depends on climate, it could be economic, it could be energy, it could be agriculture, or it could be an ecosystem. If we're looking at any system that depends on climate, if we do not take climate change into account, we are going to get the wrong answer because climate is changing. However, as scientists, we know immediately, as humans I should say, we know immediately, that any future projections are always uncertain. So the question here was, how much does this uncertainty matter and what can we do about it? We actually picked a small area to try to quantify the uncertainty as much as we could. So whenever you look at any study involving future projections, these are kind of the 4 sources of uncertainty that I tick off whenever I write about it, whenever I talk about it. The first source of uncertainty in future projections is simply natural variability. Natural cycles, the chaotic nature of our weather contribute to changes that can be very unpredictable over relatively short times. And by short times, I don't just mean a couple of days, I mean even a number of years. Here's an example. This is a picture of global temperature over the last 40 years. What I've done here is I've just picked certain little snapshots that illustrate the importance of natural variability. If you pick too short a time frame, you could get temperature trends that are flat, go up a little bit, or even go down a little bit. The reality is that when you're looking at climate change, you have to fill in the dots and you have to pick a sufficiently long time record. So we address this source of uncertainty by using at least 20 to 30 years to look at how things are going to change in the future. We cannot just look at 5 years or even 10 years. We have to use these long periods of time, otherwise we know we could end up with an answer that does not reflect the long-term change. Then we get to our climate models. We don't know exactly how the planet's going to respond to what we're putting into the atmosphere because we're conducting an experiment at a scale far greater than anything in the history of the planet. We have never done this before. We can make some educated guesses as to how sensitive the planet is, but until it happens, we don't know for sure. And as anybody who works with any type of model knows, models are imperfect. We do not have any perfect models. So how do we cope with this type of uncertainty? This could be the topic of an entire day, but in brief, we do it by trying to use a lot of different climate models because we can't say which one is necessarily better than another unless we spend about 2 years analyzing the large-scale dynamics over that region and how they apply specifically to temperature versus precipitation. That's a lot of work. If we don't have those resources, then we can simply use a fair amount of climate models because a number of studies have showed that the average of lots of climate models is usually much closer to reality than any individual model. So for example, this is some work we did nearby Hubbard Brook in Delaware. We looked at the projected change in average temperature using a set of lower sensitivity models. Then we added in the medium range sensitivity models. And then we added in the higher sensitivity models. And you can see that that gives us a difference by end of century of about 5 degrees Fahrenheit between the different projections. This is scientific uncertainty in projections for this location. We have a fourth important source of uncertainty, which is future scenarios. Climate is changing because of what we're putting in the atmosphere. The one thing that is the hardest to predict is human behavior. Nearly impossible to predict. So what do? We don't try to predict it. What we do is we develop a range of future scenarios. What happens if we continue to depend on fossil fuels as our primary source of energy? That's the top line. What happens if we manage to reduce our emissions significantly, about 80% by 2050 from developing countries, and then if we manage to go to everybody having the same per capita emissions by end of century? This is the utopian scenario. And then what happens if Notice the scale there goes below 0. What happens if our emissions actually manage to drop below 0 by end of century? This is the fairy dust scenario. Worth looking at, though. We like to be optimists.
Fairy dust.
So we compare what might be likely to happen under the higher scenario with what might be likely to happen under a lower scenario. I'm not that optimistic, so I tend to use the blue one more than the green one. And so in this way, we can at least quantify the uncertainty due to human activities. Here's why we decided to zoom in on Hubbard Brook, though. There's 2 more sources of uncertainty that, to my knowledge, we hardly ever look at. That is, what type of downscaling model do we use to get down to the local scale? And the second is, what type of observations do we use to train the downscaling model? Usually, we use whatever the heck we can get. But at Hubbard Brook, we actually had the luxury of a bit of time, a bit of resources, to look at the effect of using different observations and to look at the effect of using different downscaling methods and see how that compared with the other uncertainties that we had back here. So here's our experimental design. We were putting this together before Christmas, and this really reminded me of the 12 Days of Christmas. You know, you have 1 study area, 2 sets of observations, 3 downscaling methods. We actually had 4 global climate models, but then we didn't have 5 scenarios, we just did 2. Kind of fell down on that part. Here's the key. We used 2 different sets of observations. One was individual weather station data, and one was gridded data at 1/8 of a degree, which is somewhere around 10 miles at that latitude, 10 to 12 miles square. We also used a super simple downscaling method, a moderately complex downscaling method, and a much more complex downscaling method. So this is really simple, medium, and more complicated. Here's what Hubbard Brook looks like. There's a picture of the actual watershed. You can see how small it is.
How many miles by how many miles, north and east, west?
That's a good question. I think it's covered by about 6 to 8 grid cells in our gridded data set. So no more than that. So it's no more than
6 to 8
yeah,
cells.
somewhere around, I'm going to say somewhere around like 15 to 30 miles. Not very big. We use 2 different data sets. Here's the actual weather station data that they have at the location. And then we also used a set of gridded data. That's what it looks like over the whole Northeast. Here's the thing though, this is just a single location, right? And so if you look at the park, I mean, the single location is just somewhere in there. So what's happening down here is actually going to be quite different than what's happening up here. And that is basically what we found. So downscaling methods, this is a very simple method where you just take the distribution of daily values and you shift them this way to get warmer or wetter. You shift them that way to get cooler or drier. This is the medium complexity method where you actually basically calculate a fudge factor, so to speak, for each point along the distribution and forcibly fix the model so it actually looks like the observations. Every little dot you move by X amount. And then the last method that's a bit more complicated is you take the historical observed, or historical temperature, for example, and you rank it from the very coldest day to the very hottest day. Then you take the observations and you rank them from the very coldest day to the very hottest day, and you fit a function to it. The function can be linear, it can be a piecewise regression. We've used polynomials, but they tend to behave badly at the tails, so we've not used that here. So bottom line, do scenarios matter? They do, especially as you go out farther in time. Compare these boxes here. So this is just looking at the average of all of the different models, but looking at the difference between scenarios. There's a big difference, more than 5 degrees. Do scenarios and models matter? This is looking at heavy precipitation, precipitation over 1 inch. This is a lower scenario, this is the higher scenario. The whiskers are the uncertainty due to the climate models. So this is the uncertainty due to the scenarios, and this is the uncertainty due to the models within it. So as you go out towards the tails, you can see that the uncertainty in the models gets a bit bigger. But you can still see that all the models show an increase in heavy precipitation. No, actually, correction. All but probably about one model show an increase in heavy precipitation under lower, and all of them show an increase under higher. What about the observations? Now the plots are getting a little bit complicated, so bear with me here. What we've got here is this is using the weather station, and this is using the gridded data. This is looking at historical, and this is looking at future. Actually, correction, this is all historical. This is the station, this is the grid. This is the station, this is the grid. This is the complicated method, the medium method, and the simple method. If that makes sense, yes, I'm missing a couple of knots. Okay. What we see here is that the observations don't really matter when we're looking at mean annual temperature, and the downscaling method doesn't really matter either, and this makes us feel good. Because this means that whatever you pick out of the hat, you're going to get about the same answer, and that's great. That means the results are very robust for mean annual temperature, to whatever downscaling method you use and whatever observations you use. Let's dig a little deeper. Here we're looking at growing season. Same thing, historical, future, stations, grids. Now there's a difference. There's a big difference between whether we use the station or the grid, but the relative difference is the same in the future. So in other words, if you care about the exact date when the growing season begins or ends, you're going to get a different answer depending on if you use station or grid. But if all you care about is how much it changes over time, you'll get the same answer still. It's still good news.
Is your answer the mean of those, like in that one right there, the difference, so when you had the big black double arrow, and that is a distance?
It's the mean.
Okay.
It's between, yeah, actually that arrow should go down a little bit to be the mean. Excel doesn't draw those arrows, you have to eyeball them yourself. We see, interestingly, this is looking at the wettest day of the year. So this is the amount of precipitation on the wettest day of the year. Again, we don't have the simple downscaling method here because it doesn't, you can't really use it for this extreme a variable. So now we've just got the more complicated method and the medium range method. Now we see that between the stations and the grids, the changes are actually proportionally, they still scale, but proportionally. So the arrows aren't the same size. The difference is getting bigger over time. So now we're starting to get a bit worried about what we should be using. And then when we start looking at something like days over 100, or days over 90 degrees, I should say, which are quite rare in New Hampshire, not very rare here. Now we're seeing that the climate models, again, remember these whiskers are the climate models? The climate models have a big influence, but we're also starting to see a breakdown between the downscaling methods, especially in the grid versus the station. So this is a pretty big difference here. You're looking at 12 to 18, depending on the downscaling method that you use. This is the simpler method. This is the more complicated method. So if you're using a simpler method, you're actually getting bigger changes than if you use the more complicated method. So that was a lot of information to throw at you, but here's the bottom line that we're finding. We're finding that scenarios are important. They have a big impact on the uncertainty in temperature and extreme precipitation, especially the farther out in time you go, because the difference in our emissions gets bigger over time. The climate model that you use and the downscaling model that you use has a big impact, especially in extreme events. So this is where you want to be careful what you're using, especially with the downscaling method. Interestingly, we found that the changes become more sensitive to the climate model if the downscaling method's too simple. So in other words, the results are more robust if you're using a more complicated downscaling method that actually resolves the tails of the distribution. Observations do matter if you care about absolute values. If all you care about is the relative change, you're going to be okay with a lot of things. Maybe not extreme precipitation, but you'll be okay with many, many variables. But if your model, your application actually needs the real value, like if it matters to you if it's 34 degrees Fahrenheit versus 32, or if it matters to you if it's 2.2 inches versus 2.8 inches in that day, then the observations matter a lot, And you have to pick those carefully in terms of what impacts you're looking at, what observations matter to you. And that's not the choice I can make. That's the choice that has to be made by the people who are using this information. So the implications are that future projections are uncertain because we can't predict human behavior and we can't predict the response of the climate system to what we put in the atmosphere. But they can actually be wrong if we use inappropriate downscaling methods that are too simple, that don't resolve the tails of the distribution, or use observations that actually don't reflect the real weather conditions over that location because they're averaged too much over space. These errors here become more important the smaller the area you look at and the more variable the topography and therefore the climate of that area. So if you're looking at an area that is flat as a pancake or an area that's extremely large, then these are not going to be so important. If you're looking at an area that is quite small and also has a lot of topographical variation, then the observations you use matter and the downscaling methods you use matters quite a bit. And so what we're actually doing next is we're shoving all this information into a full hydrochemical model, and we're actually calculating the impact of this on stream flow, on net primary production, on nitrogen and carbon cycling in the forest, to try to see, do the future impacts depend on these different sources of uncertainty? What's the most important thing if we're looking at forest health to resolve in the list that we have here? I don't know the answer yet, but we can do that next year. Thank you. All right, we have time for one question, then we'll end on time.
So when you talk about the downscaling, you mean you change the resolution of your input data, or?
Yeah, it's using either a statistical or a dynamical model to basically take large-scale fields that come out of a global model and to translate them into the spatial and sometimes the temporal scale that you need to use as input to whatever you're doing.
So what you did here, basically you change the grid data is like only several pixels in your study area, right? And you're using downscaling to basically decompose this grid into a fine resolution.
Yes, and you do it in an intelligent way by using observations at a higher spatial scale than the grid. So you're not just doing some type of linear interpolation.
Yeah.
You're actually introducing more information. Yeah,
So
exactly.
that's actually a quite important question in the spatial analysis as well.
Yes.
Because modified area unit problem, so it's kind of one of the, when we look at the maps, I'm from geoscience, by the way, I'm studying spatial analysis. And we change the resolution, and from the county level data, you're going to like the city level data, the conclusion you get probably sometimes can be reversed. So
That's exactly what we're trying to figure out here is if you actually, you could even get a different sign of your conclusion if you don't have information at the right resolution. Yeah.
And in spatial analysis, we have quite commonly used method to dealing with this sort of stuff as well.
Interesting.
Might be connecting to your downscaling method you're using.
Yeah, I'd like to hear more. Thanks. Great. Well, thank you for coming, everybody. We'll see you the first Tuesday of March at 11 a.m. Thanks.